Alright, so I've already discussed the idea of how to find average velocity using a position versus time graph. So if we have our two data points, the slope of the line drawn between those two data points is the average velocity between those two data points. Because our rise is our position, our change in position or displacement, and our run here is change in time. Now what happens if instead of wanting to find the average velocity between two points, you want to know what the velocity is at one particular moment. So at whatever time this corresponds to, you want to know what the velocity is at that particular moment. Now what we could do is we could place our two data points as close as possible together symmetrically on either side of the point of interest and find the average velocity. And that would be a fairly good approximation depending upon the delineation of your graph. However, we can do this more precisely by using a little bit more math. So I emphasize the concept here where we want our two data points to be as close together as possible because we want to know what the velocity is at this particular time t. So essentially we want the delta t here to go to 0 because we want to be at one particular moment. So between t1 and t2 we don't want any space. And that is what we call taking a limit. So we can find the instantaneous velocity at some time t by taking the limit as delta t goes to 0 of delta d over delta t. Or we could just take a first derivative. Now I want to emphasize here, because velocity is a vector, once again we have to treat x and y separately. So you would take the first derivative of your x position vector and the first derivative of your y position vector, and that will give you your x and y components of your velocity at that particular time t, and from there you need to use some trig to find magnitude and direction. So if I were to ask you to find the velocity at one particular moment, I would have to first provide you then the position function. So you would see in the problem x of t equals some function, and then I would tell you at what time I want to know what the velocity is, and you would take the first derivative of the function provided, plug in t, and solve for velocity. Now I do want to take a second here to emphasize a little bit about this form of derivative. Some calculus courses use primes a lot. I don't like using primes because it doesn't tell you what you're taking the derivative in terms of. So this is the actual derivative indication. You have your d here and then your d on the bottom, and the t here indicates you're taking the time derivative. If this was an x down here, you take the derivative in terms of x. So this is, once again, an equation telling you what you're doing. So you know from the equal sign that you're going to get the velocity as a function of time. And then this here is telling you what you're taking the derivative in terms of. So if we're doing the x component of the velocity, we would take the derivative of the x position function. So that's why that is in here. And then the t down here is telling you to take the time derivative rather than taking the derivative in terms of x. And you definitely want what your function is in terms of to match what you're taking the derivative in terms of.